Hi everybody, welcome back. In this video we're going to continue with the UNet architecture, and this time we'll be training the model on the CamVid dataset, which contains 32 classes. Most of the code in this notebook is identical to previous notebooks, but there are a few small differences that we'll highlight as we scroll through the first portion of this notebook. So let's start with the training and data configuration parameters. The original images from the CamVid dataset are 960 by 720. But that's a rather large image size to use, which would consume a lot of resources and slow down training quite a bit. So instead, we'll start with a baseline case with a reduced image size of 256 by 256 as indicated below. But just to be clear, we don't need to use a square image size as we have here. If we wanted to use a rectangular, scaled down version of the image, we can do that since most segmentation models allow for this flexibility. Although when choosing the width and the height for this model, the value should be divisible by 16. Notice that we've specified a batch size of 8, although you could increase this to 16 or probably 32. However, in future notebooks, when we start taking a look at using higher resolution images, you'll need to be careful about making sure that the batch size is small enough so that you don't run into memory limitations on Google Colab. So we just wanted to highlight this particular setting as something to be aware of in general, and especially if you experience any runtime errors when trying to train your models. We already know that the UNet model will probably take some time to train, so we're going to train the model for a couple of hundred epochs, and we're also going to use a fairly small learning rate of 0.0001. So next, let's continue on to the dataset description. We've already reviewed this in some detail in the introductory notebook to this module, but we just wanted to highlight the fact that this is a very small data set with only 370 training samples, and notice that many of the classes only represent a very small portion of the data set. So we would expect the small size of the data set and the large number of classes, and the fact that they're very disproportionate, to make this a very difficult segmentation problem. Also further compounded by the fact that we're using smaller size images in this first example. The next area that we'd like to talk about briefly is the data augmentation settings in the custom data loader class. Here we're using horizontal flipping, scaling, and translation, which we think makes sense for a car-mounted camera, but we're specifically excluding rotation because we're not expecting rotation as a degree of freedom in any of the validation or test images. So just be aware that this is one area within the class that may require some tuning depending on the dataset that you're working with. And when we start using the underwater dataset in a future notebook, we'll come back to this function and make a few small changes. And at that time, we'll definitely want to include rotation since we expect a lot of variation in the camera orientation relative to the subject matter. And then continuing on to the helper functions and utilities, the only other section of code that's different from the other notebooks is, of course, the color mapping dictionary that maps class IDs to specific colors. So here you can see the specific dictionary that's defined for the data set, but other than that, the remainder of the code in this notebook is essentially the same as in the previous notebooks. So next, let's scroll down and take a look at a few of the training images just to get a little bit more familiar with the content. Notice that some of the classes actually have a very small pixel area. For example, the class associated with poles, like this light post in the image, comprise just a very small fraction of the total image area. We also wanted to point out that the quality of the lighting in many of these images is very poor, which further makes this a pretty challenging data set. Keep in mind that we're looking at the actual images and the corresponding ground truth maps. But when we take a look at the results further below in the notebook, we'll see just how challenging some of these images are. Also, just a reminder that in this notebook, we're going to be using the custom mean IOU accuracy metric and custom dice loss function that we developed earlier in the module. And you can see that we've specified both of those in the compile command. So next, let's skip ahead to have a look at the training plots. There's a couple of things to notice right off the bat. The first thing is that the model seems to take quite a long time to train, and then after about 90 to 100 epochs, it's apparent that the model's validation accuracy is leveling off quite a bit, while the training accuracy continues to climb. So this may indicate that the model is starting to overfit the training data, and this would especially be evident if the validation loss starts increasing. This may also be due to the model's limited capacity to learn well enough and therefore generalize to perform equally well on the validation dataset. It is possible that if you experiment with data augmentation, you could improve the situation a little bit, but one of the underlying problems here is that the training set is quite small. And further, even though the validation accuracy is 90%, this is likely due to the large number of pixels associated with classes that are relatively easy to identify, like the sky and the road, for example. But if you look at the mean IOU, you'll see that it's only at about 46%, which still has a lot of room for improvement. Generally, values between 60 and 70% mean IOU are considered pretty good, and anything above 70% is considered very good. But with segmentation problems, it's also really helpful to take a look at the visual results to get a better feel for how things are performing and also what the failure cases look like. So let's go ahead and take a look at that next. Keep in mind that as we scroll through these images, we're trying to compare the ground truth maps with the predicted maps, which are shown in the second and third columns respectively. But it's also helpful to view the predicted segmentation map overlaid on the original image as shown in the fourth column. At first glance, the predicted segmentation maps look pretty good overall, but because there's so many classes, you really have to pay close attention to get a better idea of how things are performing and which classes are more difficult to detect. One thing that does stand out is that the classes that are typically larger and more prevalent throughout the data set are detected more reliably than some of the smaller classes that have much less representation in the data set. And this would make sense because there's fewer examples from those classes for the model to learn from. So for example, bicyclists represent less than 1% of the data, while roads, buildings, skies, and trees represent over 75% of the data. And so this is one reason why the predicted segmentation maps do look pretty good, because the prominent classes constitute roughly 75% of the image area. But when they're measured in terms of mean IOU, which is not biased by the number of pixels in each class, we're getting less than 50% accuracy. So that's just something to keep in mind when you're studying results like these. And to get a better appreciation for some of these results, we have another function that we've implemented that will display a larger version of the predictions overlaid on the original image. And just to show you another way that you can perform inference, we decided to implement this function to process images directly from the file system. So this function takes 3 required arguments, which are the path names for the images and the ground truth mass, and then the third argument is the trained model. So first we're going to use the glob method to retrieve the list of images and mass, and then we're going to loop over a select number of images. Notice that we've added a variable here called num frames to skip, and the reason for that is since these images are taken from a video sequence, there's a lot of repetition, and therefore to provide a little more variety in the output, we're only going to process every 4th image. So we're not going to go through all this code in a lot of detail, but one thing we did want to point out is that you can pass the input image directly to the trained model, and this will return the predicted segmentation map. And then the rest of this code is just using some of the existing convenience functions that we've already developed and talked about to display the results in the notebook. So in this next code cell, we're calling the function and we're passing in the path names for the validation folders and also the trained model, as well as the number of images to process. Recall that this data set does have test images, so that if you wanted to execute this function on the test images, you could simply change the path names accordingly. So let's go ahead and take a look at a few examples at a larger scale. In this first example, you can see the predicted segmentation map overlaid on the original image. Looks like it does a pretty nice job with most of the classes in the image. For example, the larger classes are segmented pretty well, and even the 3 people in the left-hand portion of the image are captured with fairly good accuracy. Notice one thing that is missing is the pole underneath the stoplight, and there's also a small section of the car on the right that is misclassified. But those are pretty minor errors, and overall this is a pretty nice example. So next, let's scroll down here a little bit further to an example that isn't quite so good. This is an image of a gas station, and notice just how cluttered that scene is with so many different shapes and textures that involve at least, looks like 6 different classes. So it's not surprising that this is a very difficult image to segment, and even though the accuracy isn't that good, you can see that the model does do a pretty nice job of at least segmenting the cars in that portion of the image. So one thing you'll find as you experiment with segmentation models is that there's going to be a lot of variance in the results, And even if you improve the overall accuracy of a model, there will be cases where a particular image might actually have a lower accuracy with the better model, because there's so many nuances associated with image segmentation. For example, certain classes could be influencing the results. And depending on your application, you may actually want to do some additional processing to better understand what the accuracy is for specific classes. So that's all we wanted to cover in this video. In the next video coming up, we're going to introduce a third model called DeepLab v3+. Thanks so much, and we'll see you next time.